Welcome to one of the hardest calculus problems I've seen for a level 2 calculus paper. This question is quite difficult because it includes a bit of geometry, a bit of calculus, and some challenging algebra. But here we are, let's go through it together. So this question is in two parts. The first one, they've given us values for this problem, whereas in the second part, they've asked us to generalize. So what we do in this first part will help us a lot in the second part. Alright, so this problem, we are designing a house, wonderful. However, sadly, it needs to fit underneath a parabola. Alright, I guess the architect must have enjoyed their level 2 calculus class. And we're given that the apex, right, the turning point at C is at a height of 9, right, 0,9. We're also given that the points A and B must lie on the parabola, where the equation for the parabola is y equals 9 minus x squared. In other words, the height of AF or BE is 9 minus x squared, where x is the horizontal distance, right, from the center to F. And our task is to find the height of the walls, so AF or BE, to maximize the area, the cross-sectional area of the house. So it's asking us to maximize something, so we know it's an optimization problem. We are maximizing the area, so we're going to need an equation for the area, in this case in terms of x, to maximize that area. Alright, so where do we start? Area of this cross section. So looking at it, we could split it into a triangle and a rectangle. You could also split it down the middle and you'll get a trapezium, and then you multiply it by 2. Or you could split that up further into a triangle and a rectangle and then multiply both of those by 2. However you do it, doesn't matter. For us, how should we do it? I think the mark scheme does it big triangle, big rectangle, so let's do it a bit different, just to show you that either way works. I will split it down the middle and focus on the trapezium section, but I will further split it up into the triangle and the rectangle. Alright, so for part 1, the rectangle, so area of the rectangle, we know it's base times height, where base is the x value of f, right? So that base is our x value. The height is the y value, which we know is 9 minus x squared. So as our equation, we could write x times y. However, I'll just skip the step and substitute in 9 minus x squared. And the reason why we want this is so our area is in terms of one variable. Alright, that's it. That's the area of that rectangle. Now looking at the triangle, we know it's half times base times height, where the base is x. Now the height is this section right here, which is, we know the very top is at 9. Right, this distance here is 9. And from that we will subtract y, right, 9 minus x squared. So the height of the triangle is the total height, right, of the house, 9, but we subtract the wall height, 9 minus x squared. And that will simplify down a bit to half times x. 9 minus 9 gives 0. Negative times negative x squared gives positive x squared, which leaves us with a half x cubed. And actually the area of the rectangle, we could write that as 9x minus x cubed. Okay, so that's the area of those two sections, but let's find the total area, capital T, which is 2 lots of the triangles plus 2 lots of the rectangles. So that becomes 2 times 9x minus x cubed plus 2 times half x cubed. So that's 18x minus 2x cubed plus x cubed, leaving us with 18x minus x cubed. So that's the area of this cross-sectional face. Now, again, optimization problem. To maximize this, we would say maximum or minimum, right, the turning point, when the gradient is equal to 0. So let's find the gradient function. So the derivative of 18x with respect to x is 18. The derivative of negative x cubed with respect to x is negative 3 times x squared. And we set that equal to 0 because we want to find the x values of the turning points. So adding 3x squared to both sides, dividing both sides by 3, and square rooting gives x equals the square root of 6. Alright, so what does that mean? That means when this x value is at the value square root of 6, we will either be at a minimum or maximum area. Right, and just looking at our solution, right, when we square root, we get a positive and a negative. So the positive solution will be the maximum, but we need to justify that in a moment. Before we get there, the question asked us to find the height of the wall. So far, we've found the x value. So to get the height, a reminder that the height of the wall, y, is 9 minus x squared. So substituting in our value for x, we will get the height. So finding the height, 9 minus x squared, where x is positive or negative root 6, right? It doesn't matter because when we square that, the answer will be positive 6, and we're left with 9 minus 6 to give 3. So therefore height of wall for maximum area is 3. Now, how do we justify that that is a maximum? You have many options. I'll show you one of them, which you might not have learned in class yet. It's called the second derivative test. And basically, this is a way that we can check if a point, so a given x value, is either a maximum or a minimum. So the test is as follows. So if the second derivative of the area is positive, then it is a minimum. If the second derivative is negative, then it is a maximum. So that's what we're hoping for. And just bonus, if it is equal to 0, it's what we call a point of inflection. Right, but we're hoping that it will be the second one. And so to use this test, we need the second derivative. So a reminder, we've worked out the first derivative. So the second derivative will be the derivative of 18 is 0. The derivative of minus 3x squared is minus 6x. And when x equals root 6, the second derivative would be minus 6 root 6. and that is a negative number, right? It's less than 0, it's negative. Therefore, maximum at x equals square root of 6. Now, if we instead substituted in negative root 6, we would have got negative 6 times negative root 6, which would be a positive number, so that would be the minimum. Right? But since we got a negative using the second derivative test, we can conclude or justify that it is a maximum. Another way to justify it is our area of the total area equation is a cubic, and it is a negative cubic. Negative. Which means the shape will look like that, where the minimum has a lower x value than the maximum. So thinking back to our two solutions, we got negative root 6 and positive root 6. So the negative root 6 would correspond to the minimum, whereas the positive root 6 would correspond to the maximum. So you could reason about it like that as well. So to summarize this question, it is a long one. We started off by acknowledging it's an optimization problem and we're maximizing area. So we had to find the equation for area. We split it up into smaller pieces, right? A rectangle and a triangle, and then doubled it because it's symmetrical. So that gave us the equation for area. Since we're trying to maximize area, we then differentiated it, right? And in doing that, that is the achieved component. To find the maximum or minimum, we set it equal to 0 and solved for x. And in our case, we got positive or negative square root of 6. However, the question asked us find the height to maximize the area, so we had to use the relationship y equals 9 minus x squared with our x values to find the height of 3. Now that's not quite enough for excellence. We had to then justify that it was indeed a maximum for that x value and that y value. So I showed you the second derivative test where we calculate the second derivative, substitute in our x value of the supposed maximum, and since the outcome was negative, we can conclude it is a maximum. Alternatively, we could acknowledge that the area is a negative cubic, so the minimum occurs for the turning point with the lower x value, so negative root 6, and a maximum for the greater x value at positive root 6. And that, together with the height being 3, would give you excellence for this part of the question. Oh, quick break, have some popcorn, and we'll move on to part 2 right now. Okay, popcorn's in hand, let's go. So, exactly the same problem, except with more algebra, right? Because instead of giving us this as a fixed point or a height of 9, it's now at a height of d, right? Some distance. And instead of like the 9 minus x squared, we have this parameter k, which basically just tells us, is it a very wide house or a very narrow house? Right, the scaling factor. The question a little bit different down here though. Instead of finding the height that's maximum, we're trying to find that the maximum area occurs when this rectangular section, when that area is equal to the triangular section. Alright, so again, maximizing, so be thinking we're going to need the equation for area and we're going to need the derivative. So let's start there. So since we're trying to compare the two different areas, the triangular and the rectangular area, let's start off by just writing those equations out separately. So for area of triangle, what do we have? So we know half times base times height. So like the previous question, x is along the x-axis, so the base is 2x, right? That's the full width. What is this height? A to F. Well, the height is y, right? Height is y. So that simplifies to x, y. Now, we should, of course, express it just in terms of x, so that we can then differentiate with respect to x. So that will become x times d minus kx squared, or dx minus kx cubed. So that is the area of the triangular section ABC. For the rectangular section, we know area of a rectangle, base times height. Our base is 2x, and our height is y. In other words, our height is 2x times d minus kx squared, which if we expanded it out, 2dx minus 2kx cubed. So we found expressions for area of the triangle and area of the rectangle. Well, one of them is incorrect. Hopefully you spotted it. Spot it yet? Yep, so our area of a triangle, I took half times base times height. I took the height as y. However, looking a bit more closely, our height is actually d, right, the total height, minus y. So the total height d minus y. So let's fix that up. D minus y, which becomes, so d and y was d minus kx squared. So d minus d gives 0, negative kx squared times negative 1, positive, so we're left with kx cubed. Alright, good thing I caught that. Hope you did too. But so now, fingers crossed, we have the equation for the triangle area and rectangle area. So let's combine them. So the total area is, what is that? So 2dx, kx cubed minus 2kx cubed is minus kx cubed. Alright, so we have the total area of the shape in terms of x. Now we want to maximize the area, so we need to find the derivative. So the derivative of 2dx with respect to x is 2d. The derivative of minus kx cubed with respect to x is minus 3kx squared. Alright, and we set that equal to 0 because we want to find the x values of the turning point. So adding 3kx squared to both sides, dividing both sides by 3k, and then square rooting. So 2d over 3k square root. And from the previous problem, we know that there's going to be a positive and negative solution, but the positive solution will correspond to the maximum. Alright, now rereading the question, we need to now show that for this x value, the areas of the triangular section and rectangular section are equal. So, sort of two approaches from here. We could substitute our x value directly into these equations here, right, the area equations, and then use our algebra skills to show that they're equal, or we could actually find out the y and substitute it up here. Now they are equivalent, but I think substituting in for y will make the algebra a little bit easier. So if you want a challenge, I encourage you substitute in our value for x into our area equations here and here. However, I'm going to show substituting it in for y. So reminder, y equals d minus kx squared. Yep. So substituting x into here, we get y equals 2d over 3k, square root squared, so that just becomes 2d over 3k. The k's will cancel. D minus 2/3 of a d is 1/3 of a d, or d over 3. Alright. So now I will use those two equations for area. So area of a triangle, x times d minus y. Cool. And area of a rectangle, 2xy. Running out of room here. So what we're doing now is we've found the x value of the minimum or maximum. I've substituted it in for x into the equation of y. So now I know that y equals d over 3. I will now substitute x and y into our equations for the area. And what we're trying to do is show that the areas of the triangular section equal the areas of the rectangular section. So from here, it's just algebra. So x is 2d over 3k square root, all times d minus d over 3. So that's 3d over 3 minus d over 3, which leaves 2d over 3, times the square root of 2d over 3k. Alright, and I'll just stop there. You could take it further, but let's see what the other expression looks like. So area of rectangle, 2 times x, where x is 2d over 3k square root, and then y is d over 3. Well, 2 times d over 3 gives 2d over 3, and then we're left with the square root of 2d on 3k. And actually, that's all we need. Right, we've shown that the areas of the triangular and rectangular section are equivalent. So therefore, area of rectangular section equals area of triangular section for x equals the square root of 2d on 3k, which corresponds to maximum area. Right, and that is because we differentiated area and set it equal to 0. So that will give us the turning points. Cool, so just to recap this question. Again, in my opinion, one of the harder calculus problems I've come across, just because it, requires geometry knowledge and algebra knowledge in addition to calculus knowledge. So this question was a generalization problem. It was still optimization though. So we first found the area equations for the rectangular section and the triangular section. In this case, we did them a bit separate because we saw the question is asking us to check that they are equal at the end, right? So having the two distinct equations was helpful. We also left it in terms of y initially, and that helped with the final simplification. We then combined them to find the total area, and then differentiated it because it's an optimization problem, right? And that would be the achieved component. We then set it equal to 0, and we solved for x. Right, with that x value, or those x values, right, plus or minus, correspond to the turning points. In other words, the maximum and minimum areas. Just to help us simplify the algebra, we also found the y value, which then let us find the area using the x and y values. And we found that both of the areas equal 2d over 3 times the square root of 2d on 3k. Now, you didn't need to use the y value. You could have used the x value with the area equations just in terms of x to get the same result. All right, I encourage you to try that. But once we showed that they were equivalent, right, the hard bit is to know when to stop simplifying. So do them side by side and hopefully they meet early on. Then we wrote a short conclusion to say that they are equal when x is that value which corresponds to a maximum area. Right, and by showing that they are equal, that is excellence. Whew. All right, go get some more popcorn, have a study break, and I'll see you next time.